RF Man here. Today I'm going to continue with my discussion on Class E amplifiers explained. This will be part 3, which will focus specifically on the Class E amplifier and the design topology and some of the tools that are available online to calculate the specific component values needed to achieve Class E operation. So a little bit of background and history. Nathan Sokol first introduced the Class E amplifier way back in 1975. He was able to demonstrate the operation that could achieve a theoretical efficiency of 100%. And he developed a set of design equations that he published in a number of different white papers. The more recent one is titled Class E RF Amplifiers, and that was published in the CEX January-February 2001 release. And later on, Frederick Raab, he realized the benefits of Sokol's innovative design, and he expanded on his work and developed additional design equations that allowed for you to change the duty cycle and conduction angle. So these are basically the two pioneers who developed the design equations and documented the results, wrote a number of white papers. There were others involved in this design as well, but these are the two mainstream engineers who were involved in the initial work. So what are the advantages of Class E? Well, like the Class B, it provides a single transistor with a simple compact design. It's suitable for RF applications. As I already mentioned, it has a theoretical efficiency of 100%. It has lower harmonics than a Class AB or Class C, and it has extremely low quiescent current. Remember, it's biased at cutoff or just slightly above. So we're going to go ahead and design a Class E amplifier using a single IRF 510 MOSFET transistor. The power requirements will be 30 watts. The frequency will be the same as the Class B at 13.56 megahertz. It will, of course, be Class E operation. Our target efficiency will be 90% or above, and we're still operating this at 24 volts into a 50 ohm load. So that's basic design requirements. So here's the circuitry that's been well documented and published. And basically what we have is we have our switch, which in this case is a MOSFET transistor. We have an RF choke, which you typically see in many RF designs. Then we have a shunt capacitor. Then we have a phase shifting inductor, then a high Q resonator, and then our standard type of matching, which is just a simple L network to transform the load resistance into 50 ohms. So that's the basic topology. We're going to go into a little bit more detail about that. And all of these components together are typically referred to as a load network. So you'll hear me refer to the circuitry as a load network as we move forward in the presentation. So remember, with the Class B amplifier, we had a lot of overlap as the transistor turned on and turned off between the voltage and the current. And anywhere that these overlap, we have switching losses. And the switching losses basically translate to power dissipation, wasted power, and temperature rise. So we want to be able to go from this design over to a design where we're able to shift the voltage and achieve 0 volt switching. So there is no overlap between the voltage and the current, okay, during turn on and during turn off. So the only thing we have is conduction loss. There is no switching loss in an ideal Class E amplifier. So this is basically how the circuit works. Our switch again is the MOSFET transistor. So when we say open or closed, closed is on, open is off. So when we close the switch and the transistor is on, we conduct current through the RF choke to ground. Okay, so eventually it flows from the choke to the switch to ground. When the switch opens, the energy stored in the RF choke, that magnetic field collapses, and that causes current, that causes that energy to flow through the inductor and through what we call a high Q resonator, our matching circuit, and then our load. So that's where the RF power comes in. It also flows in and charges up the shunt capacitor. So that's what happens as the switch or transistor turns on and turns off. Now, LO, basically, this shifts the phase between the voltage and the current to achieve 0-volt switching. So that's what you see here. The voltage, VDS, is out of phase with IDS. So the voltage drops to 0 first before the current rises. Therefore, there is no overlap during this crossover. We call this 0-volt switching. You see the voltage is 0 before the current rises. Okay, and then the resonator helps to shape the waveform so that when it turns off, you can see again that there's no overlap. So it's a high Q resonator, consists of CO and XL, and it basically creates a short for the fundamental frequency. So basically low impedance for the fundamental frequency, but an open for the harmonics. And the harmonics are reflected back to the transistor, which help shape this waveform. This would be the odd harmonics. Okay, and then we have a standard L network as our matching circuit. So to achieve the impedance transformation, we need to go from the load impedance to our standard 50 ohm load. Now the shunt capacitor helps to increase the width of the off pulse as the capacitor charges by conducting current when the switch is open. So that's the job of the shunt capacitor. So that's basically how it works. LO shifts the voltage and the current. The resonator shapes the waveform, and then the matching circuit matches us to 50 ohms. Okay, so I mentioned that the resonator has to be high Q. Well, what does that mean, right? Well, the Q is nothing more than the inductive reactance divided by the resistance. So if you have a high amount of resistance, say in the windings of the inductor, then you're going to have basically a low Q, okay? And you can see by this drawing that, okay, the lower Q gives us a flatter response and a much broader bandwidth, whereas the higher Q gives us a much greater response and a narrower bandwidth. So typically in these circuits, we're using a Q of 5. I use that in the pi network, and I'll also use that when we go ahead and calculate the component values for the Class E amplifier. So basically, the higher the resistance, the lower the Q, and the lower value of Q increases the energy loss and heat dissipation. So if we have a high amount of resistance due to the windings in the inductor, we're going to have more loss, more heat dissipation, and a wider bandwidth. In this case, we want a narrower bandwidth to improve circuit performance. So how do we do that? You'll see in the actual circuit that I'm using an inductor that's wound on a powdered iron core. And we'll take a look at the circuit as we move on here. Okay, so some other comments about Class E. Yes, it's a single-ended power supply, and I already named the components that are used: single transistor, shunt capacitance, a series LC resonator, the load, and then the biasing and matching circuitry. Okay, basically the transistor is acting as a switch now. It's not operating in the linear region like a linear amplifier. It's switching on and off between cutoff and saturation So it acts as a switch. Typically, the drain current's about 3.5 times higher than VDD, so you have to make sure you select a component that has a high breakdown voltage that gives you enough design margin so you don't overstress the device. The operating frequency has to be greater than the resonant frequency, so we'll see some calculations about that. The shunt capacitor that we showed on the schematic, let me go back to that for a minute. Okay, this can be an external capacitor, but it can also be in addition to the output capacitance of the transistor. So when you do the calculation, for example, in this particular case, the IR F510 has an output capacitance of 81 picofarads. You would subtract that from the calculated value when we go ahead and determine what the value should be. We'll go back to that. So yeah, you take into account the output capacitance of the transistor, and you're combining the internal and external capacitance. And again, the amplifier acts as a switching amplifier and drives the load network. The load network consisting of the shunt capacitor, CO, LO, and R. Okay, and basically you need to ensure that you're achieving 0-volt switching and that there's no overlap between the voltage and the current, which provides a theoretical efficiency of 100%. So I'll leave that up there for a second. You might want to take a screenshot, but these are some of the more important requirements for Class E. Okay, so this is the typical circuit that's in a lot of the publications. It's the circuit that we just looked at. These are basically the design equations that Sokol released. The original equations back in 1975 were refined and updated. The most recent ones are in his QXE article that I mentioned earlier. And as you do your own research on this, you're going to find a lot of white papers on the topic, and you're also going to find the original releases from 1975 on. And you're going to see a lot of different variations in the equations, but when you do the math, for example, this set of equations is exactly the same as this set. They're just in different forms. So when you go through the calculations, you're going to realize that. What I've done is I've created a spreadsheet that uses the design equations that were published in the QEX Expo publication, January, February 2001. And that's available out on the internet, and I'll show you a link to that. So that's basically what most people who've developed their own tools or online tools, spreadsheets, are using, this set of equations. But again, you might see a lot of different variations. Okay, so now this is the actual tool that I use. This is online, and it's a free download. So yeah, it's easy to use, and we're going to get into that discussion in a few minutes. I also created a spreadsheet of my own using the set of design equations that we just looked at. And excuse me a moment here, a little technical difficulty. Okay, using the design equations that we just looked at, and I basically built a spreadsheet that performs those same calculations. Okay, now, just for completeness, we're going to be looking at a single-ended Class E amplifier, but there's a lot of different versions of this. You can have a push-pull amplifier. Here's what the load network would look like in a push-pull configuration for each transistor. So you're using half the value of L and 2 times the value of C. Here is another push-pull example, but this one has the load network on the output side of the RF transformer. The other one was on the input side. Here's a parallel circuit, again, with load networks as shown. But what we're going to focus on is the single-ended Class E amplifier. This is more of the traditional amplifier that we see in a lot of the publications. So we're going to go out here and open the tool. Here we are. This is available as a free download online. It matches most of the other tools that are out there. There seems to be a lot of confusion about the different sets of design equations, and I think that's because Sokol and another individual that I already mentioned, Dr. Rab, they had different sets of equations. Real brief, Rab's equations, he allowed for using duty cycles other than 50% and conduction angles less than or greater than 180 degrees. So his equations are a little bit more complex, and I actually have an example of that that we'll look at briefly as we move on here. Okay, so this is Nathan Sokol's set of design equations. This is the online tool. So basically, you'd enter in your frequency here in hertz. So what do we say? 1356. Okay, a power requirement we said was 30 watts. And supply voltage is 24. The saturation voltage for this transistor when it's fully on is 0.5 volts. So that one's easy. We said we're using a Q of 5. That's the default here. And the fall time for this device, if you look at the specification, the data sheet is 5. That's not that critical. In fact, doesn't really change any of the values, okay, other than the value of the RF choke. Okay, so here we are. Basically, it calculates the values real time as you're entering in the numbers. So it shows the shunt capacitance at 258 picofarads, sorry. Again, you'd have to subtract the output capacitance from the transistor, which is 81 picofarads. And then it shows 332 picofarads and 558 nanohenries for the resonator. And then it shows our load is 9.5 ohms. So this software will also calculate the L network values to transform 5.9 ohms, which is needed to achieve the 30 watts. I already discussed that in the Class B amplifier section. Okay, this will calculate the L network values. Just click on that, and you see our L network is 230 nanohenries for the inductor, and the shunt capacitor is 484. Now, it also gives you the total inductance. So basically, series inductors add, so you can just use a single inductor here with 788 nanohenries. That simplifies the design. Okay, and then we're into a 50 ohm load. So this tool works really well. It'll also export it to LT Spice, and you can run some simulations on it. It shows a square wave on the input, also shows a perfect switch. So when you run some simulations on this with the perfect switch, you will see the ideal waveform. But when you replace that perfect switch with a model of the IRF 510, you're going to see the waveform changes because you've got all the parasitic effects of the transistor. Remember, in a transistor, we have input capacitance, input inductance, we have output capacitance, output inductance. So all of these are considered in the model, and they do affect the shape of the waveform. So that's the calculation and how it's done. Again, an online tool that can be used, and it's downloadable free of charge. So I would suggest that you go ahead and use that and explore the different capabilities. So here I show with the L network, and I show the original load. And again, the 230 nanohenry inductor and the 484 picofarad capacitor. First, it's a low-pass filter, and second, it takes care of the impedance transformation from 9.5 ohms to 50 ohms. I also show the calculation here for the resonator. Okay, the circuit is operating at 13.56 megahertz, but the resonator is actually tuned below that. And there's two impedances to this circuit, not to get too technical, trying to keep the math relatively simple, but there's one impedance when the transistor is closed and on, and another impedance when the transistor is open and off. But we don't need to really concern ourselves with that. Also, this calculates the value of the RF choke, but this is a minimum value, so you can go beyond that if you like. And yeah, I've experimented with several different values for the RFC, and a lot of publications say it's not critical, and that's what I basically found as well. Okay, so that concludes this segment, part 3 of how to design a Class E amplifier and some of the tools that are available to do that. If anybody's interested in my spreadsheet, I'd be happy to send it to you. Just contact me. And contact information is on my YouTube channel, and I'll be happy to send it. On the next section, we're going to take a look again at the design tool, and then we're going to look at some of the SPICE simulations, and then we'll look at the actual circuit to see what the results are, and we'll at the end of the presentation calculate the efficiencies and compare it to the Class B topology. And before I go, this is a look at the Class B amplifier. Here is the RF choke. This is the shunt capacitor. I also put a variable capacitor in there so that I could optimize the value. This is the resonator here, and then the matching circuit. And again, we had two inductors in series, so I just combined them into a single inductor, and this would be considered a high Q inductor with the powdered iron core. So that's what the circuit looks like, and we'll be looking at this in LT Spice and then doing some bench testing and efficiency calculations while we're monitoring the temperature. And we'll have a lot of good data to do a direct comparison of how this performs against the Class B amplifier. So that's it for part 3, RF Man.